Okay, so in the last video, we defined a curve, a closed rectifiable curve homotopic to 0. Okay, so gamma is a closed rectifiable curve in G. Gamma is a homotopic to 0, trivial, basically trivial. If gamma is homotopic to a constant curve. What is a constant curve? Constant curve just means the trace is just a point. All the gamma t is always equal to a. Okay, like it's like you can shrink your gamma to a point. Every point on the gamma can be shrinked to this point. Then this gamma is called a homotopic to 0, and we denote like gamma homotopic to 0. Gamma is homotopic to 0. Okay, and then we have our important Cauchy's theorem. Important Cauchy theorem, the second version. Remember, the first version is defined by the winding number. The sum of winding number is always 0 for the exterior point. And this is the second version. So if f from G to C is an analytic function, and gamma is a closed rectifiable curve, in G such that gamma is homotopic to 0. Okay, so this is a condition. We replace that winding number equal to 0 condition by this homotopic to 0 condition. Then have the same conclusion. The integral of f along gamma is equal to 0. All right, so this is a second version. Second version, we just use this homotopic condition to replace the winding number condition. Right? Well, naturally, we're going to use the first version of Cauchy's theorem. So if, okay, so this is the statement. Now we have a lot of comments or remarks. 1. If we can prove that the gamma is homotopic to 0, this condition implies the winding number of gamma with respect to W is equal to 0 for all W in the complement of G. Then we can apply the first version of what? Of a Cauchy theorem. Right? It's just it means we just get a sufficient condition. We just get a sufficient condition, then we prove it. The advantage of this homotopy version is that sometimes it's straightforward. Sometimes you don't know what is a winding number equal to 0 or not, like if you have several curves. But for for the homotopic version, possibly you can observe if it is homotopic to a constant curve or not. Okay, so that's one possibility. Okay, so this is one way to prove it. One way to prove it. So how do we get the situation? All right. So how do we go through this? So for example, let gamma 1 be gamma, and gamma 0 be a constant curve. Okay. Okay. Of course, gamma 1 is homotopic to gamma 0. Assume capital gamma satisfies the definition of gamma 1 homotopic to gamma 0. Okay, so this is a capital gamma. So you have a gamma. This is gamma 1. You have a fixed point. This is a gamma 0, and something like this. So every time you shrink it a little bit, every time you shrink a little bit, then eventually you get a 0. And then we define what? We define h of t, a function h of t, to be the winding number of gamma t with respect to w. Okay, what is gamma t? Where gamma t of s is equal to capital gamma s of t. This t means step. This second variable means a step. At what step? This first variable means it's a variable in the curves. Okay, so gamma t of s is defined by this, and of course w is in c minus g. Okay, so we need to show that h is continuous. We need to show h is continuous on 0, 1, from 0 to 1. After, well, this one requires a proof. After that, we know h is integer valued, because it represents one in number. One in numbers are always integers. H is integer valued, h is continuous, then h is constant. H. Okay, integer valued continuous function must be a constant function, and we know that the h of 0 is the winding number of gamma 0 with respect to w. It's a fixed, constant curve. Of course, the winding number is 0. So we get h of 1 is equal to 0. So end of proof. End of proof. Well, this is an argument. This argument looks correct, but there's a one gap. What is a gap? Remember, there is a gap. When we define capital gamma, we do not assume that I actually mentioned that we do not assume that this gamma t is rectifiable. So from the definition, if you just have a abstract definition, abstract gamma, then this little gamma of t is just a continuous curve, continuous function. It may not be rectifiable. Okay, so this then your h of t is not well defined. Okay, so this is the crucial part, the gap. Well, we also mentioned that in practice, this is the theoretical difficulty, but we also claim in practice we will construct capital gamma such that little gamma of t is rectifiable. Rectifiable. Or even smooth. Okay, not just rectifiable, also smooth. But in practice, you have to have some technique, like what is a detailed structure and how do we construct this? Rectifiable or even smooth curve. Okay, so if we can do this in practice, we will fix this gap and everything will be done. And the author of the textbook mentioned this practical stuff is good for the training of the physicists and engineers. Okay, this practical detail is good for physicists. Where's the physicist? Physicist and engineer, because they are dealing with the everyday problems. They need to know how to overcome get the detailed strategy to overcome the problem. But this is not good enough for the mathematicians because it's too mechanic. It's not theory. It's not idea. Okay, idea is here. We show that gamma homotopic to 0 imply one in number equal to 0. That is the idea. Here is a technique. Okay, so in the textbook, the author wrote several paragraphs to explain his idea. Okay, let me show you what his. Shrink. Yeah, I think that's. Yes. Okay, so I'm going to just read this. This is I don't want to change the words from these paragraphs. So the statement of a theorem is not as important as its proof. Proofs are important in mathematics for several reasons, not the least of which is that a proof depends our insight into the meanings of the theorems and gives a natural delineation of the extent of the theorems validate. Most important for the education of a mathematician, it is essential to examine other proofs because they reveal methods. So the author wanted to emphasize the proof, the nice proof will give us the method, like the method to solve mathematical problems, not method to solve the daily problem. Okay, a good method is worth 1,000 theorems. Not only is this statement valid as a value adjustment, but also in a literal sense. An important method can be reused in other situations to obtain further results. Okay? Okay, so it's in the textbook. You can read about yourself. Better than me. Okay, so the author wanted to emphasize he's trying to give us the method and reusable method, not just a detailed the method to construct the gamma smooth or rectifiable. All right, so here this is this is still idea. So after the author explained his idea, his concern, he present the next theorem. It's called the Cushy theorem, third version. The third version says if gamma 0 and gamma 1 are two closed rectifiable curves in G, and gamma 0 is homotopic to gamma 1, not just homotopic to 0. Gamma 0 is homotopic to gamma 1, two curves. Then the Cauchy's theorem says the integral f along gamma 0 is equal to the integral f along gamma 1 for every function f analytic in G. Okay, so this theorem is more general than the theorem 6.6, the second version. All right, second version we get the quantity 0, but here we don't have quantity 0. Actually, we prove this integral is so-called homotopic invariant. The integral of f along gamma is a homotopic invariant. It does not change if you just continuously deform from one curve to another curve. Okay, so if there is a way to deform from gamma 0 to gamma 1, then this integral will be a constant, will not change, will be an invariant. All right, so that is the idea the author tried to emphasize. So we want to get the idea. We don't want to just say prove that one is equal to 0. If that is just the 0, 0 is 0. It's because you get the constant curve, then you will have 0. But here we say for arbitrary curve. Okay, so this 6.7 covers 6.6. Okay, it's a general result. All right, so let's see how do we prove it. Let's see. Assume we always start from the nice case and try to extend it. Assume that our capital gamma satisfy gamma 0 homotopic to gamma 1, and this is trivial, and it has a continuous second partial derivative. As derivatives. Okay, so we're talking about the best case. Of course, the best case in the remark already give us the proof of theorem 6.6, but you have to all these arguments are used to transform from good case to the general case. But here we also discuss the best case, the good case. Okay, so we have continuous second partial derivative. My bad. Second. We have continuous second partial derivatives. Then we know that the mixed second partial derivative does not depend on the order. The mixed second partial derivatives does not depend on the order. So the partial gamma over partial s partial t is equal to partial gamma partial t partial s. You can exchange the order of the partial derivative. And now let's see, we define a g of t. G of t is an integral from 0 to 1 f of gamma st partial gamma partial s st and ds. Okay, so check here. Remember, what is f along gamma? If gamma is differentiable, it is actually f gamma s d gamma s. D gamma s is gamma prime ds. So this is the same thing. So we get that g of 0, when t is equal to 0, it's just the integral of f along gamma 0. When g is equal to 1, it's an integral of f along gamma 1. Okay, so this construction is just an integral along the little gamma t, actually. If you want, you can write it this way. Okay, so this is a g of t. We're talking about the integral along each piece, each slice of this homotopy. All right. Well, of course, it's from 0 to 1, they equal. We're going to show it's a constant. To show it's a constant, we're going to do the differentiation. So by Leibniz rule, G has a continuous derivative, and you can differentiate inside. Okay, let's differentiate G. G prime of t integral 0, 1. Leibniz rule just means you can exchange the differentiation with the integration. So you're going to differentiate the internal. Internal is f prime gamma st, and then differentiate external, and then differentiate internal. Partial gamma partial t. Okay, this is a derivative of the first factor. Copy the second factor. Partial gamma partial s plus f gamma st. You differentiate the gamma, partial gamma partial s. So you will get partial square partial t partial s whole thing ds. Okay, so that's a Leibniz rule. Interchange the order of differentiation and integration. And remember, even after you do the partial differentiation, it is still a function of s and t. So you have to differentiate this partial derivative with respect to t. Okay, this is with respect to t, this is a derivative. But also, if you consider it is, let's check this one. It's a nice, smart observation. Let's check this partial derivative with respect to s. Similarly, so we differentiate f, and then we differentiate gamma. And plus, you copy the first part, the product, and differentiate the gamma, partial gamma partial t. right? So check these two stuff. Well, this is the product. Product is of course equal, and then here you use the continuous second partial derivatives condition. So these two partial derivatives are also equal because it has a continuous second partial derivative. Okay, so these two equal, here equal, so we get g prime of t is equal to 0, 1 partial as. We need as in order to apply the fundamental theorem of calculus. F gamma s t partial gamma partial t ds. All right, so we need this one. What is this? This is equal, like, integral f prime dx ab. It's fb minus fa, right? The fundamental theorem of calculus. You already have prime, so you're going to evaluate f gamma st partial gamma partial t at 0 and 1. At 0 and 1. So you will have f gamma s t is equal to 1. T is equal to 1. No, sorry, so s is equal to 1, my bad. S is equal to 1. S is equal to 1. So minus f gamma 0t partial gamma partial t 0t. Okay, so remember gamma st, which is little gamma t of s, is also a closed curve. Now actually it's rectifiable because it's differentiable. Okay, so we get these 2 points are the same. And at 0 and at 1, they are talking about the same point. Same point, it has continuous partial derivative. So at 0 and at 1, they have the same tangent line, technically. It's a smooth curve. Smooth curve, it doesn't matter which point, you will also always have tangent line. So partial gamma partial t of 0t is equal to partial gamma partial t of 1t. Okay, so these two must be the same thing. You cannot have this. This is not a continuous differentiable. It's continuous, but it's not a differentiable. At this point, it's not differentiable. Okay, so we get g prime of t. G prime of t is equal to 0 for all t between 0 and 1. So g is a constant function. G is a constant function, then we get a g0. G of 0 is equal to g1. Okay, so we are done. Well, in the best case. Okay, so what we know? We know if capital gamma has a continuous second partial derivatives, then we can go through this, and with a very, very creative observation. So you have to recall, to at least understand or even memorize this observation. Observation sometimes you will forget. Okay. All right. Now let's see the detailed proof of 6.7. In general, what we will have. 6.7. Okay, now let's see. We still have capital gamma, but this time we cannot assume it has a continuous second partial derivative. So gamma is the function in gamma 0 homotopy to gamma 1. Okay, then gamma is continuous. This is a minimum requirement. Gamma is continuous. And its domain is compact. I square is a 0, 1 cross 0, 1. I means 0, 1, the unit interval. I square is just this. I square is compact. So we have two conclusions. So gamma, capital gamma, is uniformly continuous. And its image gamma of I is compact also. The continuous image of a compact set is still compact. Okay, so when you have a compact set, as we mentioned, the distance, of course, this gamma of I2 is totally contained in G, so it does not touch the boundary. It does not touch the boundary. Once it's not touch the boundary, the distance between the gamma I square and the complement of G is strictly greater than 0. They cannot approach to each other. Okay, so we have this R. We have this R. Okay, so when we have this R, we have, it's a uniform continuous. Gamma is uniform continuous. There is an integer n such that if the modulus of the point st and minus s prime t prime, or the distance, let's say the distance of st and s prime t prime, the distance is less than 2 over n. It's less than 2 over n. When this happens, we have the distance of gamma st and the gamma prime gamma of s prime t prime is less than r. Okay, so this is a uniform continuity. Here is compactness. So we need both conditions. Uniform compactness and then uniform continuity. They are very close if the pre-image are close enough. All right. So now let's see the detailed way to do that. Okay. 0, 1. This is S direction. It's a T direction. 0, 1. So S is a variable of the curve. T is a slice. All right. We're going to divide cut them into small squares. See here, let capital ZJK be gamma of J over N, K over N. Here, JK between 0 and N. So what is that? So you have each point. This point has S coordinate J over N, T coordinate K over N, and it is mapped to the point ZJK. This point is ZJK. Okay, that's the idea. And this is here. Let me write. This is JK, J over N, K over N. j over n k over n. Then its right point, this point will be j plus 1 over n k over n, same height. And this point will be j plus 1 k plus 1, j plus 1 over n k plus 1 over n. And this point will be j over n k plus 1 over n, j over n k plus 1 over n. Okay, so I'm not going to say write over n. This is jk, j plus 1k, j plus 1k plus 1. Always keep in mind they all over n, and then j k plus 1. So that's all. It's a small squares. Okay, and the image is zjk. At each point it has image zjk. Put capital JJK to be this j over n, j plus 1 over n, cross k over n, k plus 1 over n. So this is a JJK. JJK. It's a square, small square, small square. And what is the side? The side is 1 over n. So the diameter is the square root of 2 over n. So the diameter of JJK is square root of 2 over n. Of course, it's less than 2 over n. We'll have this 2 over n. So the image gamma maps this JJK. Gamma maps this JJK possibly to this. Something like this. This one is ZJK. This one is ZJ plus 1K. This is a ZJ plus 1K plus 1. This is a ZJK plus 1. Gamma. Okay, so the image will be mapped into, okay, the diameter is less than 2 over n. So we keep this one as a center. So every point will be inside the disk. It's a big disk. Well, possibly small, but this is center. The disk has a radius r. Totally contain this. And this one is contained G. Okay, because of ZJK, whenever it's less than r, it's supposed to be totally contained in G. All right, so that's a relation. That is a relation. Okay, then keep in mind that JJK is this whole region. This region has a boundary. Let PJK be the closed polygon. What polygon? You see, sorry, not this one, this one. Closed polygon. ZJK. Here, ZJK. And ZJ plus 1K. I want counterclockwise orientation, so this one. And ZJ plus 1K plus 1. ZJ plus 1, sorry, ZJK plus 1. And back, ZJK. This polygon, the polygon in the image side. The polygon in the image side. Okay, so this is a convex set. Oh, well, the polygon, I'm talking about the polygon, not curve, my bad. This is a polygon. This is a polygon. We make them straight, Be careful, it was my bad. Okay, so it's not the original curve, it's a polygon. Original curve is really curved, but the polygon is a bunch of segments. And for the segment, we know that zj, k, zj plus 1k, zj plus 1k plus 1, zj, k plus 1, they are all inside the disk. So this polygon is also contained in the B zj, k, r, because this is a convex set. It's a convex set. Okay, now we can have the integral of f along the polygon pjk is equal to 0. Why? It's because it's inside the open disk. Whenever it's inside the open disk, analytic function has a primitive. Remember that? And the polygon is closed rectifiable. Closed polygon is closed rectifiable, so this integral is always equal to 0. We proved this. Actually, in textbook it says this is a proposition 2.15. The main reason is that it has a power series representation, then it has a primitive. All right. Okay, very good. So now you see here we are going to remember this is the domain for gamma 0. We're going to do what? And well, this is the domain of a gamma 1. We're going to like push the ladder or step up the ladder. We go step by step from gamma 0 to gamma n 1 over n to gamma 2 over n to gamma 3 over n. Every time we go one step, we will move from gamma 0 step by step to gamma 1. Okay, so here's the strategy. So let qk be the closed polygon not qk, q0, qk, it's my bad, qk, polygon 0k, that's the first one, the image of the first one, and polygon 1k, and znk. Okay, so what is this? So you have 0, 1, a bunch of points, and it may give you gamma 0. Gamma 0, then what do? We get those cutting point, not cutting point, sample point, and then we use segment to straight segment instead of a curve to connect them. Then that is a qk, the kth level. This is k, qk, gamma k. K is a 1 over n, 2 over n, 3 over n. K is 1 over n, 2 over n, 3 over n, and 0 over n, of course. 0 over n. Up to n over n. So it's from 0 to 1. From 0 to 1. All right? So we will show that integral of f along gamma 0 is equal to, every step should be proved, q0 is equal to f q 1 over n, and eventually is equal to integral f q n over n is f along gamma 1. Okay, that's the strategy. Now we have several steps. we have to show gamma, the integral along gamma 0 is equal to q0. We have to show between each levels they equal to each other, and we have to show the final step should equal to each other. From the q0 to qn 1 over n, and from q1 over n to q2 over n, they are similar. So we actually have first one, the first one, middle one, and the final one, 3 parts. And the final one and first one, they are similar. So you actually have 2 types of a proof you need to proceed. Okay, now let's see the first one. So first, we show the integral of f along gamma 0 is equal to the integral of f along q0. Okay, so it's a small piece, so I'm going to just pick up a tiny one. This one is j over n, j plus 1 over n, like from one of those segments. And curve may be like this. This is a z j0, z j plus 1 0. Okay, and the part of the polygon is like this. Part of the polygon. For this small piece, we define sigma j of t equal to gamma 0 of t for t between these two. T is from this small interval. So we just give a small name, sigma j, for this piece, a little piece of a curve. And then let's see, sigma j union the straight segment zj plus 1, 0, zj 0. Be careful, my notation may not be very good. Here, this is a comma for 2 points. This is a comma for 2 indices. Okay, so basically you go from this point to the j plus 1, 0 and go back. I don't know if it is clockwise or counterclockwise. It could be like this. It could also be like this. I don't care the orientation at this moment. This one is counterclockwise. This is clockwise. So the proof does not depend on the orientation. Okay, so this is a closed rectifiable curve in what? In BZJ0R. BZJ0R is in the disk centered at ZJ0. It is in the ZJ0R, so the integral of f analytic function along this should be 0, right? It's a closed rectifiable. Analytic function integral along it will be 0. So it has 2 parts. If we separate them, and move one part to the right side like this, and this negative sign can be cancelled if we exchange the order of initial and ending point. Okay, so we have a little piece, and the zj0, zj plus 1, 0 is exactly the same direction. So you can either, this proof tells us you can either go along this straight segment or you go along this arc. You have the same integral f. And this is a one small interval. You add all these together. So adding them. For j from 1 to n minus 1, because you have j plus 1, j is always from 0 to n minus 1. We have integral of f along gamma 0, because the union of sigma j is gamma 0 is equal to the integral of f along q0. Okay, so this is the first part. This is the first part. And the last part is actually the same as the first part. You just change the name from gamma 0 to be gamma 1, so you have the same. So similarly. We have the tail. Qn over n. So next we're going to prove them from Q1 Qj over n to Qj plus 1 over n. Okay. Well, let me stop. No, let's go through it. Okay, now let's stop it here. We'll continue the proof in the next video. Thank you.